Azure Group, Dave worked on the Microsoft Autopilot team, which won the Microsoft 2013 Technology Achievement Award for advances in cloud scale data centers. Prior to joining Autopilot project, Dave worked in industry research and academia, including 5 years in Microsoft research. Dave founded 2 startup companies in network traffic management and wireless networking. He was part of the 4D team that won the SICOM 2015 Test of Time Award for the 2005 paper that spurred the field of software-defined networking. And he was part of the Group Lens team that won 2010 ACM Systems Software Award. So that way we have today a guru of software-defined networking in front of you, and I invite all of you to join me in welcoming Dr. David Maltz from Microsoft.
Thanks very much for coming this morning. So today I'm going to take us on a story, a journey actually, which is going to cover some things, technologies that we've actually built, deployed, have in our data center system working today, and then extending beyond that to some directions that we're working on as active research. And I hope to show you by the end of this how those two things are connected and how they deal with this theme, which is that the cloud is about flexibility and about scale, but there's a fundamental tension between those two. We've often used software to achieve flexibility in the past, but when we add the scale of the cloud to that, we actually start to see some problems with software, and I'll explain how we've used hardware, FPGAs in this particular case, to actually resolve the tension between flexibility and scale. So I first have to tell you a little bit about the cloud. I'm not going to assume a lot of background here, and I apologize if you know all of this. I'll try to move through it reasonably quickly. But I have to impress on you how big the cloud is. For example, just taking Microsoft Azure, which is the public cloud that Microsoft uses to host many of our what we call first-party services, things like Office 365, Bing.com, which is Microsoft's search engine, as well as third-party services. These are web services and data mining services by the world's largest enterprises, everything from major banks down to what I like to refer to as joescarshop.com. And that's being run on a shared infrastructure with a massive network. Microsoft owns more than 50 million meters of its own fiber. We have 42 different Azure regions. When we talk about the Microsoft cloud, we are physically present in data centers all over the country. Sorry, I forget about those little dots. The ones connected by the map are the ones that are actually there. We have over 4,500 peering locations where our network interacts with other companies' networks. And we have 130 what we call edge sites. These are smaller deployments where we don't have a full data center, but we have servers available to help be close to our users and provide middleware services that give those users very low latency response times. Now, as I mentioned, the cloud is all about scale. I wish I could take you to one of our data centers so you could get a visceral sense of what cloud scale computing really is. Because I can't take you there, I'd like to show you this little architectural drawing. This outer building is the footprint of one building on one of our data centers. And this gray spot in the middle is where the IT infrastructure, the servers and the switches would all be located. Around that is a bunch of electrical and cooling equipment that provides the needed services to this IT space. And yes, what I've done is superimpose 2 full-size 737 airplanes as if they were parked in that one co-location facility where we would put servers. So if you can imagine a building large enough that you could have 2 737 airplanes parked nose to tail with plenty of room to walk around them, and that entire space filled with servers and switches, that's what I mean by cloud scale. And this is one building. When we actually go build campuses for data centers, each one of these buildings, and there are 8 just in view here, is that size. And this is just one data center. As I mentioned, we build these data centers all over the world. Here's another random photo of another random data center that I happen to pick. This one only has 4 of those currently built, but you can see we're already started construction on the next set of 4 over here. And there's a lot more space that we have around to continue to build out. And again, all of those spaces are filled with server IT infrastructure. Rack after rack of servers with flash, hard disk drive, and CPUs. And this represents one common shared infrastructure that we are then going to take and offer out to Microsoft services as well as external third-party services. And so the cloud works, the economics of the cloud work because of the scale. Because we build so massively, the actual per CPU hour that we pay to provide this infrastructure is relatively low. But the whole premise is how do we virtualize that shared infrastructure. We have to be able to take that single shared infrastructure and carve it up now so that every customer who comes to us feels like they have their own private virtual cloud in which they can run their services, completely isolated from any other customer that might be running around them. And that's really where software-defined networking first entered onto the world stage about 10 years ago or so now. Software-defined networking was the set of technologies that was used to take that single physical shared infrastructure and allow that very fine-grained carving. So I'd like to tell you a little bit about how that works. So I'll take one SDN concept that Microsoft Azure offers, and that is the notion of a virtual network, or a VNet. And the idea of a VNet is kind of what you'd imagine. If I have two customers, a green customer and a red customer that comes to Microsoft, each one of them can define as many VNets as they want. Now, the property of those VNets is that they are totally isolated from each other, and they are completely customizable. The customer can specify what kind of security groups that they want to have for each of their VNets, which sets of IP addresses should be reachable to other sets of IP addresses, which sets of IP addresses they even want to use inside their VNet. So for example, the green customer and the red customer could both decide that they want to issue their virtual machines IP addresses from the 10.1/16 subnet. So if you're familiar with IPv4 addressing, that means that all of the IP addresses are going to start with 10.1. And the red tenant could do exactly the same thing. Now in a normal IT enterprise shop, this would never be allowed because two machines with the same IP address are essentially the same machines, and packets between them, packets sent to one IP address is going to go to either of the machines. In the cloud, we can't let that happen. We have to maintain perfect isolation between our green customer and our red customer. And because their VMs, their services are deployed inside VNets, that's how we enable that. And of course, customers can specify how VNet should be connected to other deployments that they might have in an on-premises data center, in other Microsoft data centers, total flexibility. So SDN is the set of technologies that were developed to allow us to implement things like VNets. Now, before there was SDN, if you wanted to have something like a load balancer, or you wanted to have an isolated network with firewall properties around it, what you would do is you would go buy a proprietary appliance. So you would take your on-premises data center, and you would get a firewall appliance or a load balancer appliance, which would be, a bit of sheet metal, and you'd screw it into one of your racks, and you'd wire it up to your servers so that, for example, if it's a firewall, all the packets that want to get to your servers have to go through a cable that goes through that firewall appliance, and you'd apply your filtering rules in that firewall appliance that says these IP addresses should talk to those IP addresses or whatnot. Or if you wanted to load balance a bunch of traffic among multiple worker servers that you might have, you'd arrange it so all the packets going to your worker servers has to flow through that physical load balancer appliance in your data center, and it would then decide which of the downlink servers the actual customer traffic should be sent to. None of those physical-based technologies can work in the cloud because, as I showed you, we pre-build that single shared physical infrastructure. So instead, the premise of SDN was we're going to separate that physical appliance, which used to have a management layer that would be used to program the appliance, a control plane by which these appliances would talk to each other, and a data plane that would control how packets flow through the appliance, into these three separate layers. All of the data functionality we'd actually put onto the servers. So all the actual packet manipulation about should this packet be allowed through, should it be blocked by a firewall, is going to be distributed over all of the physical servers. The controllers that actually decide, should this IP address be allowed or not, are going to now turn into distributed systems that run and send instructions down to the various servers for what packets they should let through or not. And the management plane that says what virtual network should exist at all, again become large distributed systems. So for example, if you're a customer of Azure, and you want to create a new tenant inside of one of our data centers, you go to the management plane. You go to the Azure portal and say, please set me up a new VNet and create some virtual machines and connect them to that VNet. Underneath the covers, that management portal will have talked to some of our distributed systems in our control plane and say, okay, let's go out to the physical servers in our data center that have been selected to run those customers' virtual machines and actually start sending them instructions to set up firewall rules specific to that customer and that customer's traffic. Those servers that actually implement the data plane, that are going to see every packet that flows between the virtual machines, then know what access control is, what set of IP packets should be permitted and what set of IP packets should be dropped as packets flow through. And that has been the key to implementing software-defined networking. That flexibility to have 3 different layers, all of which are now implemented in software, means that whatever virtualization concept someone can come up with, whatever feature some customer can request, we can implement that in the software that drives our cloud. Let me again take VNets and show you a little bit more level of detail what's really going on. Let's say I have 2 servers in my data center, server 1 and server 2, and each of them has an IP address, which I'm showing in purple here. This is the IP addresses by which we know them. We call these the physical IP addresses. Okay? Now these servers are connected together by some shared network infrastructure I haven't bothered to draw. But hosted on these servers, on server 1, I have a green VM1 and a yellow VM1, meaning from the green customer and a yellow customer. And I have on server 2 a red VM and a green VM. Now, notice again, all of these VMs have the same IP address, 10.1.1.3. Now, if our green customer in this VM decides to send a packet to 10.1.1.3, we want to make sure that it's delivered to the other VNet the other green VM that's a part of their VNet. We can't let it get to this one or this one, even though these things are on physically shared infrastructure. How do we make that happen? Well, when the green tenant went and set up their VNet, they went and told what we call our virtual network controller distributed system that they wanted these 2 VMs to be on the same VNet. Our virtual network controller then sent policy down to the Azure VM switches, that is software we've written that runs on each of these physical servers, such that when the green VM sends a packet from its source address to the destination address of the green VM over here, it goes through this Azure virtual switch, which can do a policy lookup that'll say, the desired destination is sitting on the host, the server, with physical address 10.1.1.6, and therefore we're going to take this packet with the source and des sent by the green VM, and we're going to wrap them into a new packet. This is called encapsulation. It is essentially the fundamental primitive used to implement a lot of SDN in the cloud. And basically, we're just adding additional headers on, in this case, a GRE header, that says the green tenant is sending a packet from this source IP to this IP, and to carry it across our shared physical network, it's going to go from this server to this server. Okay, makes sense, right? When this packet is received by the virtual machine switch on the destination server, it'll do some checks to make sure, okay, yeah, I really do have a VM from the green tenant that's located here, and it really does have this customer address assigned to it, and if so, it releases that packet of the green VM. And now the green VMs are talking to each other, isolated from all the other VMs, from all the other customers that are on our network, enabled by this encapsulation primitive that our virtual machine switches are doing. Okay? That's sort of the essence of how we implement this VNet concept, which again is the essence of how we are going to virtualize that shared physical infrastructure. This is great, this is the tutorial. Let me tell you just a little bit more about how it works. So what's in that VM switch? Well, that VM switch is a layer that we call VFP. It's the virtual filtering platform. It's actually a part of Windows Server 2016. Anyone who gets a copy of 2016 has the same VM switch with the same capabilities that our Azure Cloud has. In your on-premises data center, which you can use something called Azure Stack. And basically, VFP has all sorts of transformations it can do to packets. We can rate limit packets, we can apply filters, access control lists to packets, we can encapsulate them, we can decapsulate them, we can do network address translations, all sorts of packet manipulation capabilities are possible here for every packet that's being sent or received by any of the VMs with their VNets that are hosted on that one physical server. Okay? So what's really going on at our software layer is that we have, as I mentioned before, these controllers that take like a virtual network description and program it down into VFP and populate what are essentially match action rules tables inside of VFP. So for example, that whole virtual network encapsulation trick, there's a VNet table which has rules that say if you see packets going to one particular IP address, then encapsulate them and send them to some gateway machine that might be connecting us to a customer's on-premises data center. Or for example, like the one I just showed you, if there's a packet going to a particular destination IP address, which happens to be hosted in the Azure cloud, we're going to encapsulate that packet and send it to the physical server inside the Azure data center where that destination VM is hosted. And every time a VM tries to send a packet, we're going to run it through a whole bunch of these max action tables and apply all the transformations that these rules say to the packet. And so all of the SDN capability, all the NFV, if you've heard of that, network function virtualization capabilities of the Azure cloud are implemented in this way. So there's a controller for the load balancers and the controllers for the firewalls. And each of them are essentially programming different tables inside the VFP. This is nice because it means I can have a software load balancing team and a virtual networking team that are all working on their own software features, and I don't have to get tight coordination between them because each of their separate controllers is programming a different table inside of VFP. It's a nice way to structure your software components to also then let your organization have good parallelization. Okay. And this is really how Azure works. We have this tremendous flexibility because this is all written in software running on this VM switch on the host. But there's a problem that comes with that. If I show you the RTT, the round trip time latency of two particular VMs, these are Azure VM sizes, they're fairly large VMs, I think they're 24 VMs, running Linux, if you were to do a bunch of detailed forwarding latency measurements, you would get a PDF that looks something like this. There would be one mode at around 80 microseconds, and then there's going to be a second very wide mode in latency that starts out around 200 microseconds. And you're like, this is terrible. Like, if you have two physical servers sitting next to each other in a data center, you would expect to see much, much faster latency than this. And again, as people try and build more and more high-performance applications in the cloud, these latency numbers, it turns out that P99 is up around 200, 300 microseconds. It's really hard to build a high-performance application when 1 in 1,000 packets might take a good fraction of a millisecond, 0.2, 0.3 milliseconds, just to get back and forth between two VMs. And so the question you ask is, well, why does it look like this? And the answer is software. Right? So fundamentally, we are writing all of this as software running on general purpose computers, which are hosting these VMs. And for scalability reasons and all the things that you would have looked at in an operating system class or computer architecture class, sometimes there's too much work to complete in a single schedule in Quanta, so some of that work is deferred to another schedule in Quanta, which might be scheduled 100 microseconds later. Dang, that happens more than once or twice, and that's what this mode out of 200 microseconds is coming from. And there are a whole bunch of factors that go into this, and we have really detailed conversation about that. But fundamentally, you run a system using software, this is the kind of stuff that you're going to see. Again, the 50th percentile of packets, the latency isn't too bad. 80 microseconds, that's pretty typical. Simply crossing the TCP/IP stack in a Linux server, if you do a physical server, it's going to take you about 30 microseconds. So you've got 60 microseconds on each end just there in sort of the client's VM stack. It's really this long tail, though, that causes problems. The question is, what can we do to fix that? And again, part of the larger story is software and this notion of using VM switches to implement SDN worked fine when servers had 1 gig NICs. And it worked pretty okay when servers had 10 gig NICs. But all of our servers have 40 and 50 gig NICs now. And we're going to 100 gig NICs within the next year or so. And when you get to these higher and higher speeds, the customer expectation, the service application architect expectation, is that they are going to see faster and faster latencies. But the problem is that tail latencies, whenever you have software, are long. And what we need to do is we need to find ways of basically leveraging this faster hardware and essentially get the speeds of hardware consistent with this hardware while still having the flexibility to go and implement new functionality all the time. Because on any given week, I get a request for a new virtual networking feature or a new load balancing feature or some new cool capability of the cloud that some customer wants, and I and my team are expected to deliver that. So the real question is, how can we get the performance of hardware? Hardware has been rapiding up very fast. Hardware tends to have very deterministic latencies while still having the flexibility of software. Okay, the ability to implement new features whenever we dream them up, not just at the time the hardware was being designed. And so that led I and my team to this notion of using FPGA, which is a way of doing a reconfigurable hardware offload engine for these SDN features. Let me tell you a little bit about how it works. Essentially what we did is we went to every server in our fleet, and while there used to be one physical network interface controller there, a NIC, what we did is we put an FPGA right next to it. So packets, data that a CPU wants to send are going to be first delivered over a PCIe bus to the NIC, and then they're going to be transmitted as Ethernet frames. And those Ethernet frames, we're actually going to run them through this FPGA, which can then do whatever kind of transformations on the Ethernet frame we might want, before the Ethernet frame is then sent on to the top rack switch and the rest of the network, the rest of the shared infrastructure. And that FPGA, turns out, is also connected to the CPU via PCIe bus. And we've been doing this for quite a long time. And the essence of our solution is we're going to use this FPGA to implement the SDN functionalities, because in doing so, we can get deterministic performance, deterministic latency and high performance while still being programmable. Here's what we've done. So as I showed you in the previous slide, we have a whole bunch of controllers which are all going and writing data into these match action tables inside of VFP. And the first time that a VM running on one of our servers tries to send a packet, it's going to go through this software path. And essentially what we're going to do is we're going to keep track of which rules from each of these tables applied to packets of that flow. We're going to kind of combine them or compile them together into a single meta rule that applies all the actions of all the rules that match that particular flow. And then we're going to take that combined rule and we're going to offload it to something we call a generalized flow table that we've implemented in the FPGA on our SmartNIC. Okay. So each of the various transformations and is this packet allowed or should it be dropped, we figure out what has to be done for all the packets in that flow. We offload that then into a piece of FPGA hardware that we've created, or an FPGA circuit on our hardware. And now every subsequent packet sent by this VM as part of that flow doesn't need to go through the software path. It can be given directly to the NIC and then run through the FPGA, which will apply all the appropriate transformations to that packet. This is called SRIOV, Single Resource I/O Virtualization. And the fact that we can do in our FPGA everything that our software could have done up here is what's going to enable us to then move this functionality down and see performance improvements. Essentially what we're doing is before, where with VM1 needed to send a packet to VM2, it would have to go through a virtual software switch on the first server, then go to a physical NIC, go across our physical shared network, up through a physical NIC, through another software switch, and then to the VM. The packets can now go directly from the VM to the physical NIC across our network and back to the destination VM, because essentially this NIC itself is applying all the packet transformations necessary to implement this SDN strategy, this SDN visualization. And it's been a huge win. So I'm very proud to be able to claim that Azure does have the fastest network in the cloud, the fastest NIC in the cloud. You get our larger VM sizes, you are guaranteed to get 25 gigabits per second running to VM to VM. It's got the lowest latency of any of the cloud providers. Turns out that making this change for us saw a 10x latency improvement. And that latency improvement turned into real workload improvements. Whenever you do micro benchmarks, people can often say, oh, look, 10x latency improvement, but it might not actually make a difference to customers. These differences made real differences to customers. So for example, SQL databases were able to handle twice as many I/O operations per second as a result of these latency reductions that they were previously. And that's real money and real better performance that our customers are getting. So we've been very happy for this feature set, which is known as Azure Accelerated Networking. Going back to slightly the more quantitative view of what happened, this orange graph is the graph I showed you before of the latency we saw without accelerated networking. When we turn on accelerated networking, not only does the mode, the P50, drop down to about 25 microseconds, but you can see what's happened to the tail. The tail is essentially gone. And the reason for that is because FPGAs are essentially a hardware pipeline, and that hardware pipeline has very deterministic latency. And cool things are happening. We have a new version of our NIC, 50 gigabit version coming out. This is where the QSFP cages that would plug into the top of rack switch, the FPGA is hidden under here, and then there's still a physically separate NIC chip, which is underneath that heatsink there. This is a card that was actually designed and built by Microsoft. And I can tell you a little bit more now about sort of why FPGAs and why we might want to be using FPGAs. So showing you things that we really built, that stuff's deployed, you can go to Azure today and turn it on. I'm going to tell you about some other things we've done with FPGAs and why we're interested in them next. So the world is getting bigger and bigger. It's clear. The amount of data we have to process is increasing continuously. That's very clear. If you go look at some of the estimates, in 2013 there was about 4.4 zettabytes of data being produced a year. By the year 2020, which is only 2 years from now, we're going to be up to 10x that, 44 zettabytes. This is a dramatic increase in total amount of data. What do people want to do with this data? All sorts of stuff. One of the big drivers in this increase in data, as you heard in the previous 5G talk, has been video. Video is being consumed everywhere, it's being produced everywhere. People want to do automatic analysis of it, a lot of machine learning, face recognition, object recognition, remote driving scenarios, automatic drone delivery scenarios. A lot of that stuff requires processing huge amounts of data at very low latency. If I have a car driving down the road, I have a deterministic amount of time to make a decision. Is that a stop sign that I need to stop for or not? Is that a pedestrian in the way that I need to avoid or not? And throughput. I have to do a lot of these kinds of inferences every second as I'm going into these new kinds of applications that people are thinking about. And so if we start thinking about this kind of new AI-driven, machine learning-driven world, the question is what platform is the right one to build those services on top of? And I kind of have the four standard candidates here. I have a general purpose CPU, I have GPUs, graphical processing units, I have FPGAs, and I have custom ASICs. And I've laid them out on one dimension of which you can compare these, which is from most flexible to least flexible, and from most efficient to least efficient. Looking under the covers a little bit, the CPU has a very fixed architecture, general purpose control unit, general purpose registers, general purpose arithmetic logic unit, general purpose stored program computer. If you look at the GPU, what I essentially see is a very, very large array of very small CPUs. So I can do work in a very data parallel kind of way. If you look at an ASIC, I have combinatorial logic essentially, connected together by a bunch of buffers and retimers and FIFO queues as necessary. But the circuitry is completely fixed from the time I design it and lay down the masks, and I can't change it. And FPGAs represent kind of a hybrid between the sort of CPU, GPU, and the ASIC in that I get to have combinatorial logic, but I get to program what the tables in that combinatorial logic are, and I get to reconfigure the connections, the buses between that combinatorial logic as I want. If I peek into what an FPGA is in a little more detail, if you're not familiar with that technology, essentially what I typically have is, I'll get some hard cores. Often it's an ARM core, so not a super powerful general purpose CPU, but a general purpose CPU, where really what I get is I get this sea of programmable gates, essentially a logic gate that can have any truth table that you want, and the ability to then route buses between those truth tables however you want. And intermixed around those, I might have some digital signal processors and some memory blocks and other kinds of things. And this essentially is what I'm going to build my FPGA logic out of. if you want to think about comparing a CPU and an FPGA, if you think about a CPU, I essentially run a variable stream of instructions through the CPU processing engine, and then I run a variable stream of data through there. Whereas comparison with the FPGA, I have to fix the instructions that I'm going to run at the time that I program the FPGA, but then I'm very data parallel, and I can run multiple streams of data through that instructions in a pipeline, hardware pipeline fashion. I get the deterministic latency of that hardware pipeline as a result. Now, I showed you some nice graphs of how FPGAs were able to accelerate SDN for us and things like that. All of these stories, it sounds like, oh, it's their great win. We've been working on this for a while. The first time you try something, it never works, and you got to keep at it. So we actually did our first SmartNIC, our first FPGA efforts back in 2011 with what we call our Catapult V2, and then over the subsequent years, we did revision after revision after revision, learning from each one, until we eventually got to the point that we have this hardware platform that we have today. And what we essentially are doing today is if you look at each of our servers, we typically run dual sockets, so I have two general purpose CPUs, each with memory connected to them. One of the CPUs connected to a physical NIC, which has this QSFP cable that I showed you, essentially goes over and connects to our FPGA. And then that FPGA is also connected by a PCIe to one of the CPUs, so that packets that are sent by CPU go through the NIC, go across this cable's Ethernet frames into our FPGA, we process them, and then out across the QSFP. Now, why do we do it this way? This is clearly not the most efficient way, because again, when we first tried this, many people thought it was going to fail. And so the one thing I couldn't do is deploy a bunch of FPGAs into our data centers and then have that make our servers not useful. FPGAs are expensive, but this rest of the server is really, really expensive. And so when we decided to go try this at the first time, we put this cable in under the theory that if worse came to worse and I couldn't get the FPGA program working, we were simply going to have our staff in the data centers pull all of these little jumper cables here, plug the top rack switch directly into the NIC, and then we'd have a server connected to a top rack switch network just like it always was, and I wouldn't have a job because I would have wasted lots of the company's money, but at least that the fleet could go on and proceed. But it just sort of shows you the kinds of trade-offs you have to make as you're trying to get a new technology out into the field. But the end result is we now have this ability to modify in our FPGA every packet sent or received by an ARVM. And we have a bunch of FPGAs that are directly connected to our high-speed shared network. And it's this next thing that we're going to start leveraging in interesting ways. Because as I mentioned before, machine learning and AI is extremely data intensive. And a lot of the kinds of operations we want to do in AI are very friendly, particularly deep neural network inference, to implementation on an FPGA. So I assume most people here are familiar with the basics of machine learning and AI now. If you haven't seen some of this, I encourage spending some time. It is really, I think, one of the things that's changing our field very, very deeply. Even those of us who have backgrounds in communications are often being called on to apply that knowledge of communications to AI and machine learning problems. It turns out that one of the most common types of inference being used in AI today is called a deep neural network. It looks roughly like this. You can think of this notion of multiple layers of neurons. Each of one is taking inputs from the left, applying a summation and weighting function to it, and then pushing its output to the neurons in the next layer, and this goes on and goes on. The interesting thing about this is that you can do things like take a bunch of pictures, feed them to the input neurons, and then through a training process, which is often done on GPUs, figure out how to train all of the weights so that each tier in this DNN starts picking out different features of the incoming images, and ultimately later tiers will start to recognize individual aspects of this is a face, this is an ear, this is Alice, this is Bob. And so finally coming out of the end of your neural network, you can actually have labeled, tagged data of what, for example, might have been seen in an incoming video stream. Well, training this up is the training problem, and as I mentioned, that is particularly well done with GPUs. But actually doing inference, when I have a real-time video streaming through, and now what I want to do is actually run every pixel of that video image through this deep neural network to see if Alice or Bob is present in that video. This is the kind of thing that FPGAs are really, really good at. Because what this deep neural network essentially is, it's a combinatorial logic circuit with a bunch of weighting functions in it. And so what we found is by taking FPGAs and starting to use them as part of our inference, we've been able to do extremely well. So for example, we can do inference about 10 times better using FPGAs than we can using CPUs and GPUs. And again, it's because the deep neural network inference problem happens to match particularly well to the kinds of hardware pipelines that I can build in an FPGA. And it's still flexible, so that if I need a hardware pipeline or if I need a combinatorial logic pipeline, it's different than what I wanted for deep neural network, but for some other kind of classification problem, I can just go and reprogram the FPGA. That's the nice thing about it. That combinatorial logic can be transformed simply by loading a new configuration onto it in the same way that you would load a new program into a general purpose CPU. So the hardware that I've built and deployed is now useful for any kind of AI or ML problem, the ones we know about today, as well as the ones that are coming in the future. Just like I put that FPGA out there because I knew I had some SDN functionality I had to accelerate today, and I didn't know what kind of SDN functionality I was going to have to accelerate in the future. So I couldn't go build a custom ASIC for that. I needed the flexibility the FPGA was going to give me. And again, scale. Because we went in and put an FPGA in every one of our servers, because we wanted to use them to accelerate networking transformation functions, that encapsulation and decapsulation, I have this tremendously large fleet of FPGAs connected to servers that I can now start to use the unused gates on those FPGAs to do interesting and novel machine learning things. So for example, I apologize, I had to strip the numbers off of the X and Y axis here, but the X axis is queries per second, the Y axis is query latencies at what we call the 3 nines percentile, or 99.9 percentile, so the speed of the slowest 1 in 1,000 query. This is on an inference problem that's actually part of the Bing web search engine. This is the scatter plot of orange dots is what we saw when we were using software. You can see that the number, the query latency is generally higher than the scatter dot of blue, which is the inference on the same kind of data input when I'm using FPGAs. The maximum queries per second that we can handle with the FPGA is significantly higher than what we could handle with the software. And again, the grouping, the distribution of latency is much tighter when running on an inference on an FPGA than when running on the software. Again, that deterministic latency that we get by using a hardware pipeline. If I show you now some more graphs, this is actually taken from part of the inferencing layer again in the index search portions of the Bing search engine. This top series of graphs shows you the 3 nines latency for FPGA, significantly less than what we see with software. And again, and most importantly, all those outlier spikes are essentially gone. Nice deterministic latency. This is super important because again, if your application is driving a car down the road, it's not okay to run somebody over just because the inference to see whether there was a stop sign in the picture or not happened to take a little bit longer that time. We need the deterministic latency. Interesting graph you see down here. This is now run over, this is a couple of weeks worth of data here. Sorry, a couple of days worth of data. The blue line is the average FPGA query load. The red line here is the average load for queries being handled by our software pipeline. This interesting thing happened that we didn't expect but was kind of fun. We stood up an inference, a web search backend that used the FPGAs, and when the rest of it was running software, and there's a load balancing system that decides how many queries to send to each of the potential backends. And that load balancing system, without us telling it anything, realized that the FPGA backends were processing way more queries per second at much lower latencies than the software. So they automatically shifted a whole bunch of load over onto the FPGAs, which is why the load on the FPGAs is much higher than on the software. That's sort of a nice, cool thing that we're seeing. Again, switching to these new architectures made enough of a difference that actually changed how our software architects, our application architects, started to think about designing their applications. New things became possible once they had this capability. Okay. So, again, continuing the story, I started off talking about some very concrete things. How do I build a virtualized network optimization infrastructure? And then I talked a little about FPGAs and how they're applicable to problems like deep neural networks and machine inference. I showed you a little bit of data from that. I'm now going to go into the completely speculative world. I'm going to tell you about some things that we think are possible, but we're actually just starting to work on as research. And that is, how would we take this concept of using FPGAs and combining them into a cloud platform to create something that we call hardware microservices. So, today, my team or another team inside of Microsoft can go and program those FPGAs and create hardware accelerated services that then other people can use. But we would like to democratize this. We would like it to be the case that any customer could come to Azure and say, hey, I have a problem that would be better optimized with something like an FPGA hardware pipeline. I would like you, Azure, to take this and program it into your FPGAs and make it available to me. Essentially, take those FPGAs and add them into my virtual network. Yet another capability that SDN would be able to give us. So essentially, customer's tenant would then be a combination of a bunch of management software, which might run on general purpose VMs, hardware, FPGA gates, and the circuits, the FPGA logic that we'll get from the customers themselves that are run on that FPGA, all connected by the super low latency shared network that Microsoft built to connect all the servers in our data centers. In the ideal world, like I say, a customer would come to us with some kind of model. Maybe it's deep neural network, maybe it's something else. And they would have taken their model and translated it into essentially an FPGA pipeline. What we would then do is take that FPGA pipeline, described as a circuit, FPGA circuit, and potentially one bigger than can fit onto any one FPGA that we happen to have in our data center. But our tooling would then take that and figure out how to refactor it into multiple FPGA circuits which could be split across the FPGAs on all the servers in our data centers. So essentially, we're going to take in this big circuit that they've envisioned, figure out how to partition it and spread it across our infrastructure so that it fits in the gates we have available. And then that becomes the pipeline which we would then connect into their virtual network that they could then push data through for doing inference. And that's how we plan on creating these FPGA-powered services that would be hosted in Azure. This is why, going back to the picture I showed you before, it was important that we created a system that had FPGAs directly connected to the top of rack switch. Because in this new model of hardware microservices, it's going to be the case that not every packet deep crossing our network is coming from the CPUs. It's going to be the case that a CPU might try and send a packet, which would then be received by the FPGA, potentially on another server. That FPGA may actually do some amount of processing on the data that's in that packet. And if it needs to then go to a part of the FPGA circuit not present on this FPGA, but on the FPGA of some other server in the data center, the FPGAs themselves will take those intermediate results, package them up into a frame, send them out across the network, where they'll be received by the FPGA on the other server, unmarshaled, run through the rest of the customer's logic on that FPGA to produce the final results, which then may be put back into an Ethernet frame and sent over to a VM for processing elsewhere. So it became critically important that we had this FPGA with direct access to our physical shared network. In essence, again, if I have the customer with some kind of model that they want to go do inference on, we're going to figure out how to split it up into bits of logic which will run on each of the various FPGAs. So for example, the logic of the blue nodes might need to be split across 2 FPGAs. The orange logic might need to be split across some other number of FPGAs, so on and so forth. And essentially, each of those splits, every time that there's a FIFO queue inside the FPGA pipeline, that becomes a potential place where we could actually now split that FPGA circuit across 2 FPGAs, taking the data that was put into the FIFO on one side, packaging it into an Ethernet frame, sending it across the FPGA on the other side. Now, clearly, to really make this work is going to take a lot of research and development in terms of FPGA tools. We need to make sure the timing closes on this. We need to figure out how customers can give us FPGA logic, FPGA VHDL files, potentially annotated in some ways that would help us determine how to best split this, that single VHDL out across multiple FPGAs. But these are all problems that the FPGA community is currently working on, and we believe they're all solvable. The end result coming out of this is we think we're going to end up with a configurable cloud. Maybe I should say reconfigurable cloud. Where on the outer perimeter, there's a general purpose CPU compute layer. It's web services just like everybody is used to today that you can upload data to. You can do whatever sort of truly general purpose computing is necessary to prepare data. But the next layer in will be some kind of reconfigurable compute layer. That hardware offload acceleration, probably implemented using FPGAs, that will enable very deterministic latency, but very high I/O operation per second processing of the data that's coming out of that general purpose CPU layer. And then, of course, all of this needs to be connected by a very converged, high-performance, low-latency network that will enable data to transfer between all these different servers and the FPGAs there. And if we can realize this, we think that's going to get us to a world where we can really push what's possible in the cloud. Amazing things have been enabled by the cloud already, a lot of cost savings, a lot of power savings, but this is a new capability that doesn't exist even in on-premises data centers today. And this would be truly adding, I don't even know good words to describe the kinds of computing power that this would put at the fingertips of application architects as they think about trying to take us forward into a data-enabled, data-powered world. So that's something that really excites me. A lot of people at Microsoft, across the networking teams, across our AI and machine learning teams, we're all working to recognize this vision and then make it available through Azure Cloud Services. So thank you. I've had a few questions. I think they want a microphone just so everyone can hear me.
So,
Please go ahead.
so you were saying this where you could basically have these FPGAs take the different, partition the, based on the requirement, you can partition the FPGAs to take the load of the system, of the different VMs. I'm assuming that you want to do it dynamically, with changes over time.
Okay, so I understood the question to be, we want to be able to dynamically change the partitioning of functionality across the FPGAs over time. So in the world of accelerating SDN, so a very concrete thing that we've already built, there the problem is relatively simple because on the FPGA on every server, I need all of the functionality to support hardware offload of the maximum possible throughput and operations of that one server. So it's actually quite deterministic. So in the SDN case, I know exactly how large of an FPGA circuit I need in order to support the capabilities of the largest VMs I could possibly put on that server. When we end up in the hardware microservices world, where I was talking about what I discussed at the end of the talk, here now we're in a place where, yes, each FPGA will have some number of gates that are dedicated to infrastructure processing, like that SDN hardware offload I talked about at the beginning. But there are a bunch of unused gates on each of the FPGAs. And those are the things that we would now be running customer FPGA logic in. And some customer FPGA logic will be bigger than others. And so then I have a sort of a knapsack packing problem of how do I take my different customer FPGA requirements and fit them into the available set of FPGA gates that I have across all the FPGAs and all of the servers I have in my data center. Now, in terms of dynamic rebalancing, again, the nice thing about these hardware offload pipelines, even as a customer have, is that the customer will, we believe, is going to be able to tell us, look, I need so many data operations per second that I want to be able to put through this FPGA pipeline. And so we can scale and give them enough gates across enough FPGAs to produce a pipeline that can handle that many data operations per second. And then if the customer wants to scale that up, they can redeploy, and we'll then create a larger FPGA pipeline for them, spread across more FPGAs. But at the moment, we're not thinking about trying to dynamically balance this out. Again, typically here, application architects know they have a target for how many data operations per second they need to be able to handle. And what they want is guarantees that the underlying Azure infrastructure will deterministically meet those targets.
So I have one last question, David. So you talked in history of software-defined networking in data center and how you guys are unable to deliver the latency guarantees that are required. Then you talked about how FPGAs are helping you to achieve those latency guarantees. This is in terms of the cloud scale data centers. In the context of internet, as a guru of software-defined networking, do you have any comments to the researchers who are working on SDN? How SDN in internet and in the telecom world is going to play a big role in the future? Or are there any limitations how they can take it from your talk?
Okay, great. So inside of a hosting platform, SDN is the easier area in which to deploy. Why? Because when I go back to this slide here, essentially, the SDN layer is hidden below what we call the Azure Resource Manager. So there's a very clear declarative portal to which customers connect to say, here's how I want my virtual network to be set up, here's the load balancers I want, how all these services should be able to interact. And then from there on down, it's just Azure code talking to Azure code. And I don't have to have interoperability. One of the problems that I think we've seen as we try and take SDN into the internet context is you have multiple ISPs. So in that case, the data plane is actually owned by different organizations, each of which may have implemented different sorts of primitives. Some of them are using OVS, some of them are using VFP, different VM switches, some of them are different hardware with different capabilities. And so now there's a lot more work for each of the controllers to do to deal with the disparities of the hardware that they're working with. And when building the controller itself, you now have the organizational challenges and tensions of two ISPs, who's going to own the customer relationship, which, you don't want to have two controllers that are both trying to drive separately the state inside the data plane. Otherwise, you can end up with inconsistent state on data plane forwarding packets, and that's a very bad customer experience. So I think those are the challenges that you would see with SDN. Now, when we look at service chaining in the server providers world, where that tends to have been most successful is, again, inside of a single service provider. So AT&T can go and implement service chaining using SDN because, again, it's all within that one autonomous organizational boundary. I think SDN between service providers, I'll make a prediction. I don't think it will be successful, but not for technical reasons. For the same reason that we did not see in integrated services, diff-serve QoS take off across the internet, meaning between multiple autonomous systems. We would see those same organizational tensions and business tensions prevent success, even where technological success is probably possible. But you will see success in SDN in service chaining inside of service providers, just like we're seeing success with SDN inside of cloud hosting platforms.
One last question with respect to your Project Olympus, the OCP platform that you showed. Do you have any plans of getting FPGA into the Blade server or that architecture? Currently, it's based on x86 or I think the latest Qualcomm ARM processors, I guess.
That's right. So the OCP is the Open Compute Platform program?
Yeah.
Program, yeah. So this is basically a way of open hardware sharing between cloud service providers. Facebook and Microsoft are both very big contributors to this. And essentially, we see no value in trying to compete on the basis of our hardware platform. We'd like lots of people to use the same kinds of hardware because then it makes the cost of that hardware cheaper. So we've been giving away our hardware designs. We intend to continue to do that. There will be FPGA cards, essentially hardware designs for the things we've been doing that are coming out as part of OCP. I'll tell you that that's the good news. The bad news is just the challenge that we've had is around inside, to make the FPGA work, there's a shell of FPGA logic that has to go around that. And that today includes intellectual property that came from the actual FPGA vendor themselves. So there are a couple different FPGA camps which are kind of at war with each other. And so neither one will let us release the IP that we have with that particular vendor. So it's been hard for us to release the shell around our internal FPGA logic. And so to really make the FPGA card useful, we could give the hardware, but leaving people with just a blank FPGA to start with is probably too high a barrier for many people to be able to start working on. And that's the challenge we've had to really make it useful to the general academic and research community. But we're trying to fix it. Thank you very much.
So I think with this, we are concluding this exciting morning session. I hope all of you had many research problems for you to go and look upon. So I would like to give a small token of appreciation from NCC 2018 to Dr. David Maltz. And we are very thankful to him and also to Mr. Satish Degni for agreeing to come to NCC 2018 on short notice and making it happen on a grand scale. Okay?
There we go.